All right, welcome to a new chapter. We're going to talk about in chapter 7 single parameter hypothesis tests. Okay, so here is our goal. Hypothesis test is one of the most important applications of inferential statistics. So let's kind of start from the beginning, right? So, what is the goal of statistics? We identify our research question first. Once we know what to study, this determines the population of interest. Okay, and then this also means we decide what to measure. That means we are looking for specific parameters. Okay, so for example, let's say we want to know the proportion of US residents who agree with the president. Okay, so that's a proportion, and we would ask every US resident. That would be the population. Of course, it's usually impossible to collect and measure that parameter. However, what we do is we collect a sample. Okay, so we look at a sample here, gather data, and then once we've got the sample, we start computing statistics. So remember, the parameters would be the things we're trying to measure from the population, and statistics are the things that we are trying to measure from our sample. Okay, so of course, at this point, we know lots of things we can compute, lots of statistics like proportion, mean, standard deviation, etc. And we can summarize it, look at a histogram, we can do one variable statistics, etc. And this gives us a good idea about just the sample. What inferential statistics aims to do is, so whenever we say inferences, we're trying to learn from our sample about the population. Okay, so this is the most important step in statistics, right? From the sample, this arrow represents go back, what can we learn about the entire population? Okay, and again, that is called statistical inferences. So, all right, sorry about that. So, going back to this new chapter, so we've got hypothesis tests. In this first section, we will go over an overview here where we're going to essentially talk about all of the big key terms that we need to use in the future. So let's start off with the logic of hypothesis tests. So here we go. What is our goal? Our goal is going to be to make a decision about a parameter based on statistics. So in this chapter, we're going to look at the two parameters, proportion and the mean. So this is the same thing we did in the last chapter. Okay, and we are going to be using probability theory. What about probability theory? Well, this is where we use the sampling distribution theory. So remember, sampling distributions, why they're so important is what we are looking at is, imagine we have a sample of, let's say, 10 people. Let's say we want to know whether, let's change the research question. Let's say our research question is, do you like dogs? Okay, we want to know that about all Mount SAC students. Do you like dogs? So what I could do is I can take a sample of, let's say, 10 people, ask them, and compute the proportion. Okay, but then I'm going to do that to another group of 10 people, and then another group of 10 people, and then another group of 10 people. If I start collecting all of those sample proportions, which we write as p hat, then according to the central limit theorem, we've got that under the right assumptions, we're going to have a beautiful bell-shaped curve, and that the middle of that is going to be our population proportion. Okay, and then the same logic applies to the x bar, so for mean. So if we, let's say I say, how many siblings do you have? Okay, and then I ask a group of 10 people. I collect everyone's individual number of siblings and then take the average. That's going to give me one X bar. And then I ask another group and another, etc. And if I collect enough of them, we start to see a nice bell-shaped curve. Okay, this is why I love sampling distributions, because they are the backbone of the theory to statistics. Okay, so the key here, the key word that I underlined in our goal is to make a decision. So let's compare the two different types of inferences in chapter 7, which is what we're going to learn now, compared to what we just came from in chapter 6. So in chapter 6, our goal was to estimate whether a population fits within a certain interval. Okay, and the name we gave these things was a confidence interval, CI, right? We abbreviated it as CI. Our goal was to take our sample, use that sample to basically learn about the population, and what we did is we estimated the population parameter. Okay, and we did that for proportions and for means. What are we going to do in chapter 7? In chapter 7, it's a very different application where what we're going to say is, let's say I've got a past information about a parameter. We are going to, or we will test whether or not the parameter has changed. Okay, so we've got past information about the parameter, and we're going to test whether, so this is kind of the key word here, and this is why we call them hypothesis tests. Okay, so here's the structure. There's 3 basic steps to a hypothesis test. Number 1, we make an assumption about reality. Okay, what that means is we are going to assume, again, we have a past information. So we're going to say assume that the past parameter is the same as the now. Okay, and these are the 2 phrases I'm going to use over and over, okay? So we've got information from the past. We're going to start with our assumption that this is a great place to begin, right? We're going to say right now it's the same as the past. Okay, so for example, let's say that, 80% of people love dogs 5 years ago. Okay, that was the past proportion of people who love dogs. But we want to say, hey, 5 years is a long time ago. Let's see if now people love dogs as much as 80% from the past. Okay, so the next step is look at sample evidence. Okay, so we basically then collect sample evidence, and then we basically calculate statistics. Okay, in our example here, if we want to know whether the proportion of Mount STAC students who love dogs, okay, we're going to start with the assumption that now it's the same 80% as it was 5 years ago. Okay, but let's say I go out and I collect a brand new sample and calculate the proportion from that sample. That would be p hat. Once we've got that and we've measured it, what's the next step? After that, we determine whether it contradicts our assumption. So here's where we say we are going to test whether or not our sample statistics agree with or don't agree with, or I guess I should say contradict, because that's a good word, our previous assumption. So, right, we're going to test whether or not our sample statistics, so for example, when we've got a p-hat, does this agree with our assumption about, right, where remember our assumption was that 80% of Mount SAC students love dogs. Okay, so we're going to test whether now our new sample agrees with that or is much, much different than that. So again, in statistics, very different than in other math classes like algebra, right? We'll never be 100% certain. We'll just be able to tell if the sample data agrees, or let's say supports, a statement or not. So this is basically as good as it can get in statistics, because we're always going to have to be okay with, again, our sample is not complete information, right? Going back to this little picture here, it's always just getting a small sample of people. So we have to live with the fact that there could be a little bit of error in our conclusions. Okay, so let's go over some of the key terms here. So we are now going to talk about hypothesis statements. So we've got what's called the null hypothesis, and I'm going to write this as H0. So null hypothesis is basically 0 and null are just synonyms in science, so we use that all the time. So H for hypothesis, and then we put a little tiny 0 below. Okay, what is the null hypothesis? So this is a statement of blank or no effect, no difference, and is assumed true until there is statistical evidence that indicates otherwise. So we're going to say a statement of no change, no effect, no difference. So this is what I'm talking about when we say the past. And I keep putting quotes here because that's just one specific application of a hypothesis statement. As we progress in the chapter, we'll talk about more general ways of how we use these tests. But okay, start with the idea of we've got past information, and then we're going to just collect a new sample and compare the now versus the past. Okay, next up is what's called an alternative hypothesis. Okay, the idea here is the null hypothesis is our basic assumption. Okay, basically assume what we knew from the past until we have new evidence to change our minds. The alternative hypothesis, we write that as H for hypothesis, and I like putting it as a little a for alternative. But the alternative notation to this is, so let's say also H1. So if you watch other YouTube videos or if you read different textbooks, H1 is the other common name for an alternative hypothesis. So what is this? This is a statement we are trying to find evidence to support. Instead of the null hypothesis. Okay, so really when you do a hypothesis test, it's all about the alternative hypothesis. So we are trying to find evidence to support this. That is what our goal is. So there's 3 different types of hypothesis tests called left-tailed, two-tailed, and right-tailed. So I like using the following abbreviations. I call these left-tailed test, two-tailed test, and right-tailed tests. Okay, so that's just my own abbreviation for these since I don't want to write that full word every single time. And we're going to need to say these a bunch for the next couple weeks. All right, I'm going to start off with and zoom in on the left-tailed test. So we start off with the null hypothesis. Okay, and what we're saying is we're going to say, okay, we've got a parameter that we're trying to study. Again, in the example I keep referring to is imagine the proportion of Mount SAC students that love dogs. And we had a number from the past. Okay, so what actually I want to say is, when we write this as an equation, what are we saying when we put this in here? What we're saying is, on the left-hand side, we're saying that the now parameter, in this case, proportion, we are saying that the now proportion is equal to the past proportion. And again, and that's an assumption. That is why we call it a hypothesis. Okay, so we're going to keep this notation consistent, the now, and then when you see a number on the other side, this is the past. Okay, so that is our null hypothesis. What's our alternative hypothesis? Well, we're going to say that with a left-tailed test, we're going to say that the parameter is less than whatever the past number is, okay? And this is, again, what this says is essentially that the now, we think that the parameter now is less than the number from the past. So let's say that we think, again, 5 years was a long time ago. People loved dogs 5 years ago, so we had 80% that loved it. But we think now everyone hates dogs, so we think that the true proportion of Mount SAC students that love dogs is now much less, okay? What does it mean to be less than the past? Again, less than that 80%. So here is where we get into the theory. Okay, so I am going to draw this in red, and as if you watch my previous videos and you've come to class, you know that I draw my sampling distributions in red. We're going to label this the X-hat distribution, which is the generic name for a sampling distribution. All right, actually, give me a second. I want to, before I start drawing all over this, make a copy of it so I can kind of color code it for the other curves. What happened here? Okay, back to our left tail test. Okay, so now that we've made this alternative hypothesis where the now is less than the past, let me put some little quotes by this. That's all our alternative. What does that mean? Okay, well, again, these are two hypotheses. We make these at the very beginning before we do anything else. Okay, so now what we do is we go on, we collect a sample, a brand new sample, and then why I have a sampling distribution, because remember, this represents a dot plot. If you imagine every possible sample of a specific size, they live under this bell-shaped curve, right? This was the big result from chapter 6 on sampling distributions. So the idea is, where does our sample live? Okay, so if our sample, let me make a really big red dot, and let me put it, I don't know, over here. Actually, over here. So if our sample, that big red dot, comes from the middle part of the curve, okay, by now you should be thinking, you know what? That is where we expect most of our samples to come from, right? That's the green zone. This is what we call the usual range, right? Okay, the idea here is, what is our sampling distribution? We are basically saying, by giving us the null hypothesis, we are saying that the middle of this distribution is going to be what we call the past. Oops, I'm sorry, why did I put mean? I guess whatever our parameter is, let's call this the past. Again, I'm trying to use notation that works for all the parameters. Okay, so if once we got that parameter, basically the sampling distribution will target that. So we have basically that the pass is down the middle. So when we collect samples, remember, data varies, samples vary. So we never expect to hit that exact perfect proportion of 80%. But if the proportion of people who love dogs at Mount Sac is 80%, we expect if we collect a lot of samples, they're going to be within 80%, within that kind of green zone here, right? We expect variation. So what does it mean to actually change our minds, right? So if our sample comes from this kind of middle part of the curve, basically in this green zone, basically what we say is we say our sample is consistent with the null hypothesis. That's kind of what we're expecting if the null hypothesis is true. Okay, and then we're going to get into the language in the next page about what we say basically from there. But okay, that's one possibility. The other possibility, and again, we think that it's actually less. If you look at that dot, it is less than the pass, right? But it's less by a little bit. So maybe that's another way of saying it in this part here, right? It's less, but only by a little. So to change our minds, in statistics, we say, you know what? We expect variation, so we expect that samples could be less within this kind of green zone. So what we want is if our sample comes from over here, right? So we collect our sample and we actually get that the proportion is like 50%, right? That is way less than the 80% that's kind of in the middle. If we have something that is 50% and we basically come from this tail here, okay, this is when we say, you know what? This is strong statistical evidence that actually the proportion really did go down. So if we have our sample from this side, this is when we say, you know, there is evidence that our parameter is less. Okay, so when we say less, we mean statistically less, right? We don't mean that this green zone, we have to be much, much less. So the next question should be, okay, that makes sense. What we're really saying is, if our sample comes from there, what's basically much more likely is that there's basically a new bell-shaped curve where we think that our sample is basically much closer to the middle of that brand new bell-shaped curve. Okay, and this is kind of the bell-shaped curve of the now, which is telling us that the now parameter should be basically somewhere over here. That's essentially what it means to have our sample come far away from the middle. Basically, this is what it means to have statistical evidence that the parameter is less and it really is different. Okay, so of course the next question is, well, how do we decide where's the green versus the pink? Glad you asked. We need to have some sort of cutoff, right? Some sort of cutoff where we basically have to say, okay, this is where we draw the line, literally, between green versus pink. Okay, and this is where we use what's called a z-star, and it's called a test statistic. I'll go over that in the next section, okay? But that test statistic is essentially a critical value. This is why we've been talking about critical values for so long, but we're doing it from a slightly different perspective. Okay, so that is a left tail test. Let's go through that same logic, and again, maybe I'll go a little quicker this time. From a right tail test perspective, again, let me kind of hide all the other stuff, and let's start from the beginning. Okay, so a hypothesis test. We start with a null hypothesis where we basically say, okay, the parameter now, that's this left side, we start off assuming that the parameter now is the same as the past. That's why we have an equal sign in between. Then we have a alternative hypothesis where we're going to say, okay, we think the parameter is now bigger than whatever the number was in the past. And that's our basically competing claim, right? We've got two claims here. We think it's the same as the past, or we think it got bigger. So the now is is greater or larger, let me say larger, is larger than the past. Okay, so what do? Well, we fire up a sampling distribution where we put this line down the middle. This is basically the past parameter. Okay, if it's a proportion, let's say it's that 80% I keep talking about. And then what if dogs are even more popular now? So we suspect that, oh, actually 80%, that's not that high. We think it's like much, much higher. People love dogs even more. Okay, so again, we still put that 80% down the middle, and we still got this logic where we've got this kind of, if we collect the sampling distribution, remember this is all possible samples. Okay, if we've got a sample x bar comes from this green zone, it is bigger than the past, right? But it's kind of within the amount that we assume that data can vary, right? This is visually left to right. That is how we represent data's different. The data is varying, but not by enough for us to change our minds. Okay, and if all of the samples that are coming from over here, so if this is our x hat, our sample statistic comes from over here, this is where we go, you know what? If our sample is coming from this kind of extreme part of the tail, and in this case, because we think that the thing is now bigger, right? And if our sample is actually bigger than the past one, it's going to come from the right side. Okay, then we're saying, you know what? We think it's actually so far away from the past number, we think it's way more likely that the bell-shaped curve is actually much closer, right? We think that the new sample is coming from the middle of a brand new bell-shaped curve that is actually much larger, okay? And this is basically the now parameter. Okay, let's say that, nowadays people love dogs even more, and 90% of Mount SAC students love dogs. That 10% difference is quite large. Okay, so here is, we have to make a cutoff between the green versus the pink, okay? And this is what we call the test. I'm sorry, yeah, just, we have this cutoff. So it actually is a critical value. So call that CV for critical value, and call this CV for critical value as well. All right, well, one more hypothesis test to look at, but let's start from the very beginning, and let me try to hide as much as the other ones as I can. If we make a two-tailed test, what we are saying is we start off with the exact same assumptions as before. We say the parameter now is equal to the parameter of the past. So notice that all three null hypotheses are exactly the same. We're always just saying it's equal to the past. But we've got three different options for the alternative hypothesis. So for the alternative hypothesis, what we're saying is, in a two-tailed test, we think it changed. So I'm going to put a not equal to sign here, because what we're saying in a two-tailed test is we think it changed, but we don't know which way it changed. We don't know if it got bigger or we don't know if it got smaller. And by saying that this changed, let me write it real quick. We think that the now parameter has changed from the past. What do we mean by that? Well, let's go through to our sampling distribution. Let's pretend we look at every possible sample. That's the X hat distribution. Again, we put the middle in the past. Whatever our proportion is from the past, that is where the middle is. Okay, so if we collect our samples, right? So if our sample statistics, the X hats, we collect them and they come from the green part of this curve, right? They could get now a little bit smaller than the past or even be a little bit bigger than the past. Okay, we expect variation in data, so being a little bit away from the middle is normal if the null hypothesis is true. Of course, we make a cutoff here, and remember these are going to be critical values, so we've got the positive and negative one. And by the way, I guess since I'm fixing my mistakes, might as well put a little minus sign there because it will be negative because it's on the left tail. Okay, so if our samples come from between the two critical values, we say, okay, that's where we basically expected them to come from, so we don't change our minds. However, if our samples come from either the left or the right tail to test, right, from the right tails, sorry, then we say, you know what? If our sample comes from this extreme left over here, X hat, that means it actually did change, and it's probably way more likely that the middle is somewhere down here. It's much smaller. If our sample comes from over here, that is giving us statistical evidence that we think actually it changed and it got bigger. So two-tailed tests, they're basically, we don't really care that it's bigger or smaller. We just want to know if it's different. Okay, cool. So I am going to stop the video right here. This is page 1, just kind of setting up some key terms. I'll see you in the next one.